in the last video we finished talking about parabolas, and now we're going to move on to ellipses. These are probably new to those of you who haven't done further maths before. So let's begin from scratch. And we're going to do this video in 2 bits. We're going to do one video about the definitions associated with ellipses, and we're going to do the second video, which will follow this one, about the mathematical characteristics of ellipses, the mathematical relations which help us find particular things about ellipses. It's hard to fit all this information into one video. That's why we're doing it in 2 parts. So let's begin. What is an ellipse? An ellipse, in a nutshell, is an oval shape. It's an oval conic section. Now, the standard ellipse is like this. The standard ellipse lies sort of flat. And we'll talk about the non-standard ellipse in just a moment. But for the time being, we just want to talk about the basics. So, an ellipse is an oval shape. What are the features that we talk about, or what are we concerned with when we talk about ellipses? The first feature is the center. Alright? Just like a circle, an ellipse has a center. The standard ellipse has center 0, 0. Alright? So that's the center of an ellipse. Every ellipse has one. The second feature, the major and minor axis. Now pay attention. When we talk about ellipses, we are concerned with 2 very important maximum widths. We are concerned with the maximum width between 2 points horizontally and the maximum point between 2 points vertically. Now, in the case of the standard ellipse, you can clearly see that the maximum width horizontally is greater than the maximum width vertically. And as a result, the horizontal length, which let's show with a dashed line here, this horizontal maximum width is called the major axis because it's bigger. And consequently, this vertical maximum width is called the minor axis because it's the shorter of the 2. Now I want to just take a slight tangent to a possible non-standard ellipse, just to illustrate just to show you some of the differences that could arise. Okay? We talked about the standard ellipse being lying flat in such a way that the major axis is the horizontal axis. A possible non-standard ellipse could be one where the vertical axis is the major axis and the horizontal axis is the minor axis, because clearly, as you can see here, the maximum width vertically is much greater than the maximum width horizontally. Before we continue, actually, one thing I should say is that the center of an ellipse always lies in the middle of the major and minor axes. So in the case of the standard ellipse, the center 0, 0 will be in the middle of the minor axis and the major axis. And even with possible non-standard ellipses, the center will be halfway between, halfway across the major axis and the minor axis. Now, this is one of the ways in which you could get a non-standard ellipse. That's what I want to talk about. A possible variation on an ellipse to make it non-standard could be that the major axis is vertical rather than horizontal, as is the case in the standard. Another possible variation is that you could have a center that's not at 0, 0. You could have a center at, let's say, 1, 2. Or any numbers a, b. Just like with a circle. As we know, if you change the center of a circle from 0, 0 to anything else, it's no longer a standard circle. So I just want to illustrate some of the differences between standard and non-standard ellipses. So that takes care of the major and minor axis. What about the equation of the standard ellipse? The standard ellipse has equation x squared over a squared plus y squared over b squared is equal to 1. In this case, the x denominator, in this case a, is equal to half of the horizontal axis length. And likewise, the y denominator b is equal to half of the vertical axis. Alright, so A and B are constant half-widths of the horizontal and vertical axes respectively. This equation is telling us that if you take any point on the standard ellipse, the square of the x-coordinate divided by the square of half the horizontal axis length plus the square of the y-coordinate of that point divided by half the vertical axis length will always equal 1. A and B and 1 are constants, obviously, and x and y are variables. Now, I just want to draw your attention to something here. As we mentioned earlier, when you go from a standard to a possible non-standard conic section, the equation may change slightly. And in the case of an ellipse, this is how it might change. We talked about a possible way in which the ellipse could become non-standard by not having center at 0, 0. If that happens, then the new equation of the ellipse is this, or would be this. It would be x minus 1 squared plus, x minus 1 squared over a squared plus y minus 2 squared over b squared is equal to 1. Just like with the circle, if the center is not 0, 0, you would subtract the coordinates of the center from the respective x and y's, and that would be your new equation. Alright, one more possible variation I will point out is that when you look at the standard ellipse, you'll clearly see that the horizontal axis is longer than the vertical axis. And as a consequence, a squared will be bigger than b squared when it comes to the standard ellipse, or for that matter, any ellipse where the major axis is the horizontal axis. So if the major axis is the horizontal, a squared will always be bigger than b squared. And likewise, if the major axis is the vertical axis, as is the case with non-standard ellipses, then b squared will be greater than a squared. So it's all quite systematic and fits in reasonably nicely with each other. So we've talked now about some of the basic features of ellipses, the center, the major and minor axes, the equations, and how those features may vary slightly when it comes to standard and non-standard ellipses. Alright? Now we're going to talk about foci. We talked about the focus when it came to parabolas. Now we're going to discuss foci in the context of ellipses. Ellipses have two foci. They always lie on the major axis. Okay, so in the case of the standard ellipse, the foci would lie on the major axis, in this case the horizontal axis, and the foci are always equidistant from the center, i.e. the center is always in the middle of the distance between the two foci. If you were talking about a possible non-standard ellipse, where the vertical axis would be the major axis, the foci might be somewhere here. They would still be equidistant from the center, but they would lie on the vertical axis because that's the major axis, and the center would still be halfway between the two foci. We'll talk about how to calculate the coordinates of foci in the following video. For the time being, we just want to go over the basic features and possibly compare and contrast standard and non-standard ellipses. Feature number 5, directrices. We talked about directrices when it came to parabolas. Now, ellipses have two directrices. Now, this is where it might get just a little bit confusing. The way I think of directrices is such that the directrices of ellipses would always be perpendicular to the major axis if it were extended. Okay, so in this case, the major axis is this length here between these 2 points, but let's say you were to extend the line a bit. The directrices would be perpendicular to this if you were to extend them. Alright, so a rough sketch, these would be your directrices. They would always be perpendicular to the major axis if it were extended. So these could be two possible directrices for the standard ellipse, and again they are equidistant from the center of the ellipse along the major axis. So this distance here between the center and this directrix is the same as the distance between this center and this directrix. If you're talking about a possible non-standard ellipse which is vertically oriented, where the major axis is vertical, then the same principle would apply. If you extend the major axis a little bit, then the directrices would be perpendicular to that major axis, like so. The same principles would apply, and the directrices again would be equidistant from the center of the ellipse. So this distance would be the same as this distance here along the major axis. So we've discussed these 5 features now, and we've contrasted how these features may differ between the standard and the non-standard ellipse. Feature number 6, eccentricity. We came across eccentricity when we were talking about parabolas, and we said the eccentricity of a parabola is always 1. But what is eccentricity? What does it refer to? Eccentricity is a constant ratio for any particular ellipse. Eccentricity refers to the ratio between two distances. The first distance being the distance between a point on the ellipse and the focus, and the second distance being the distance between a point on the ellipse and the directrix. Okay? Distance number 1 between the point on the ellipse and the focus, and distance number 2, the distance between the point and the directrix. The ratio of these two distances is called eccentricity. And in the case of an ellipse, no matter what ellipse you're looking at, whether it's standard or non-standard, whatever it may be, the eccentricity of any ellipse will always be less than 1. So that covers sort of the basics of the features and definitions of ellipses. We're now going to move on to a video where we will discuss the mathematical relations behind them. Thanks for listening.